this notion of Halm. And I'm gonna jump right into proving some theorems because these things are fun. And also, I'm doing you all a favor in the sense that you will find a couple of these theorems will shortcut your homework. So you can kind of quote the stuff that I'm doing here to make it less daunting what you all have to do next for the next homework. Okay. Theorem. That was a kind of a 2-for-1. Let R be a ring, communicating with identity. The sequence of R module homomorphisms. Zero, A, B, C. Is exact if and only if for all R modules D, the sequence zero home R DA home R D D home R D C is exact. This is sometimes called covariant Halm. So notice the maps go in the same direction. So this is cool. If this is exact, and I do mean this the way it's written, I mean that F is 1-to-1 and the image of F is equal to the kernel of G. Right. I don't necessarily know. G may or may not be onto it. Right. Then you get this exactness here. So the missing piece of the puzzle is, you might say, well, Jim, what if this is also onto, if this is truly a short exact sequence, does this make this truly a short exact sequence? And the answer is no in general, right? But if the sequence is split exact, it does, right? There's also a contravariant Halm in the following sense. If A, B, C, 0, well, also, G. So now the image of F equals the kernel of G, but it's not necessarily true that F is 1-to-1. Also, this one is exact if and only if for all R modules D, the sequence 0 home R AD, no, CD home R BD R A, and this is F R. Notice this one turns this onto map sort of into a 1-to-1 map, doesn't it? Right? Kind of cool. This is called contravariant Halm. Contra, it goes in the opposite direction. Sometimes people will say Halm is a left exact functor. That means you get this left exact. It might not be exact on the right. Notice in both cases, the end game is left exact in the sense that you start with 1-to-1, but may not end with onto. Okay? So this is a fun one. I encourage you to prove the first statement yourself. I'm gonna do the fun contravariant one, right? Because I think it'd be cool to kind of see, uh, proof. Let's do the contravariant one. See if you can do the covariant one. So look, it's probably good for me to warm up. I talked about what this all means. So what we have is we have A, B, C, 0. I know the G is on to, and the image of F is kernel G. This gives, for example, you have F bar from, I'll throw G. And how does this work? Well, you have gamma, it goes from C to D. Right? And I'm going to use G to get you from B to D. So now, let's see. Gamma goes from C to D. Oops. So gamma, where's G go? G goes from B to C. So I need to do G first, and then gamma. There we go. So notice input. So my homomorphism that's induced by G is you take an input gamma that goes from C to D, and you compose it using G. So now this thing goes from B to D. Right? And in a similar vein, we have F bar from home R BD to home R AD. And if you have a tornado guy, it goes from B to D. And this gives F bar tornado is tornado F. And this now goes from A to D. We discussed the fact that these are our modular homomorphisms last time, and it's not too difficult. It's kind of a pedestrian, not too difficult. I want to get all this business though about the fact. So let's start off assuming that A, B, C, 0 is equal. Number one, show G bar from RCD into home RBD is one. This is really kind of groovy, right? Because I like doing this really kind of illustrates how you turn the onto into one-to-one. Okay, suppose gamma in home RCD is in kernel of G bar. So in other words, G bar of gamma is the 0 function. And this is gamma G. Now, our burden here is we need to show that gamma is a 0 function, right? Do I agree with that? Any ideas? And what's the ontoness of G? Is that gonna help us? So. Of course, my goal is, what I'm hoping and praying for, it's true, is that gamma is the zero function. So somehow gamma of B, I hope is zero. Can anybody see anything that might help us? What do we know about, what do we know about G? That it's onto, right? So what does that tell us about that B? Because G is onto, oh, I'm sorry, right. I want to show that G is, let me scratch through that. I want to show my goal here. Gamma, which is from C to D, is the zero map. So let's let C be in C and consider, there we go, gamma of C. There we go, much better. Now, we know that G is onto, correct? G is onto, there exists B and B such that C is G of B. Right. Now check this out. Gamma of C is gamma of of G of B, which is gamma G of B, which is C. Therefore, gamma is identically zero, and so G bar is 1. Are you okay with that? Okay, now I want to show that the image of F bar is down here. The image of G bar is contained in the kernel of F bar. That is, show this composition is 0.
Or the bottom line is like, I know the gamma of G of B is like the GB is the input. For the gamma G times B, is that like the
It's a composition.
Okay.
Right, composition gamma G evaluated at B. Now for the next bit, consider 2. We want to show that the image of G bar is contained in the kernel of F bar. Well, to this end, let gamma again be in home R CD. Right. If you look at gamma, if you look at the composition F bar G bar gamma, this is F bar of gamma G of the definition of G bar. And this is gamma GF. But the composition GF is 0 because the original sequence is exact. Therefore, F bar G bar of gamma equals 0. So the image of G bar is contained in the kernel of F bar. That is to say, when I compose the G bar and then F bar, I get 0. only one more thing to show. And the last thing to show, and this always seems to be the hardest, we want to show that the image of, well, let's do it this way, the kernel of F bar contains the image of G bar. Okay, so let's think about this here. Right. I want to show the kernel of F bars containing the image of G bar, right? So let's kind of set this up. Let me run some maps might be good here. Here's what we know. Let's let tornado the kernel vector. That is to say, F bar of tornado, which is tornado F, is the zero function. Now somehow I need to show, so let me make a parenthetical remark here. So I've got this homomorphism from B to D that goes to zero this way. It's got to come from something, right? So I need to show there exists gamma from C to D. That is some gamma here, such that G bar gamma, which is gamma G, is equal to tornado. This is my goal, right? I want to disappear. That is for this might be useful. This is exact. Okay. So you know what I want to do? I want to try to just build this thing that I need. So I've got A, B, C, 0. And what do I got here? I've got this tornado that goes from B to D. And when I do this composition, I get 0, right? When I do, this gives me 0. And somehow, I've got to find some gamma. I need to find some gamma here. So this is the diagram piece. So I need the G gamma is equal to whatever this is. Everybody cool with that? And I can use the exactness of the top row there. Any ideas? Maybe. I'm just gonna get on my tractor and define it, right? Gamma of C. I'm gonna force this thing, right? Now, the problem is, any ideas on what might be useful to help me out?
To use objective.
Oh, I don't know that. I mean, remember, this actually, we have to, this has to work for any R module.
Right.
Well, one of the big things that I know is I know that G is onto, right? And I'm gonna do this. I'm gonna say this. Here's what I mean by forcing. I've got C here, right? I know there's some B that goes to it, right? For sure. Unfortunately, there might be many of them. but there's at least one. And C's got to go down here. You know what? I'm gonna do this. I'm gonna let gamma C be tornado of B, where G of B is equal to C. Now, that should set off, well, it's a dunce cap. I will say that was gonna set off an alarm here, a little 5-alarm fire here, because what's a big potential difficulty here? Well, defining this is an issue, right? Because what have I done? I've taken C and I said, hey, you came from this B here, and I'm gonna assign, wherever B goes down here. So the big question is this well defined? All right. And the answer is yes, so that's what we'll be doing it. So, but let's figure out why that's the case. Suppose B and B prime are such that G of B equals G of B prime equals C. All right, so suppose I have two different pullbacks here. What does this mean? This means that since B and B prime go to the same place, that means G of B minus B prime must go to 0, right? And so what can we deduce from that? This is in the kernel of G, which is the image of the previous, that's right. So exactness is going to help me out here. So there exists A and A such that F of A equals B minus B prime. Now, impose this with tornado, and I get but this is equal to 0 because we made the assumption that remember, tornado was in the kernel of F bar, right? Therefore, it's a channel well defined. And that's really all you got to show. Well, showing that this is an R module homomorphism, once you know it's well defined, is pretty routine. And let me also point out that if you have let's see, if you look at G gamma of C, this is equal to oops. Oh, wait a minute, G starts at B. If you look at G gamma of B, there we go. It's better. This is, in this case, the role of C is G of B, so this is 20. So the kernel of F bar is contained in gamma G bar. And so we have equality. Any questions on it? Yes.
The step where we say that tornado at A is equal to 0, Why was that again?
because of this assumption here.
Okay.
Yeah, in fact, this function right here is identically zero.
Sure.
Yes.
What is the difference between like gamma G of B and then like gamma G? Like the difference of like the parentheses.
If I'm understanding.
It was on the-
not anything.
Other part, but like if you have like gamma and then parentheses G of B, and then you take the B
The
out.
gamma and the G are functions and the B is an element, so it's just, you're just putting different parentheses, it's just function composition.
Oh, okay.
Yeah. Other questions? Okay, so here's what we have. This animal is exact means that the Hom sequence is exact. Alright. Let's do the other one. Now suppose. And this one's kind of fun because now suppose for all R modules D, we have 0 into home R CD, home R BD into home R AD. That's GR is exact. We now need to show that this animal is exact, right? Now, you've got a little freedom here, but you gotta be clever, I think, in some places anyway. You just pick your module D right, in a certain sense. Let me remind myself here. You will show A, B, C, 0 is exact. G is onto. So let's start by showing that G is onto. Here, I am going to let D because I'm just a big fat cheater. That's what I'm gonna do. Basically, I'm gonna go through and pick my module because this holds for all our modules. Pick my module in a sagacious way to make this as easy as possible. So in the first, what I have is here. So I get 0 home R C mod MG, G bar home R B C mod MG. And I don't care after that right now. I'm trying to show that this the G is onto. So let pi from C mod MG be the natural projection. That if pi of C is little c plus mg. So this is just a natural projection onto the quotient. Just take C to its coset representative here. Everybody okay with that? This is a good old-fashioned all-American homomorphism, no problem there. Now notice that if I look at G bar of pi, this is pi G, which is 0. Just by definition, because what happens here is you start in B, and G of B is actually in the image of G. So when you project it, you project to the triple coset, right? Because, right, when you do pi G, first you take your B, G takes it into the image of G, and then it's killed in the next step. Everybody okay with that? So this is 0. But G bar is 1 to 1. Right? So pi must be the 0 homomorphism. Right? Because when I plug in pi here, I get 0. G bar is 1 to 1. That forces pi to be the 0 homomorphism. Therefore, the only way this is a 0 homomorphism is if C is equal to the image of G. Right? Because as long as there's something in C that's not in the image of G, this is not the 0 homomorphism. Right? The only way this can be the 0 homomorphism is for this quotient to be 0. Do I agree with that? That's kind of bananas, isn't it? But thinking it this way, then therefore G is onto. Because you see, the image of G is all of capital C. Everybody okay with that? Okay. Let's do the image of F is in the kernel of C, or the kernel of V. Take that kernel G. For this one, I want D to be C. And consider 1C to be the identity function. Now, if you look at F bar, now I have C and D, and I start with the identity function on C. When I do this twice, it's 0 because it's exact. That home sequence is exact. This means this is 0, but let's take this apart. By definition, this is F bar of 1CG. And by definition, this is 1CGF, which is GF. So since GF is the 0 function, the image of F is contained in the kernel of G. Any questions? And finally, last containment. In this case, I want D to be B mod the image of F. And I'm going to focus on pi from B to B mod the image of F. Again, I'm going to do sort of what I did back here. This is the canonical projection. Pi of B is the coset B plus image of F. Notice that this is a very similar thing to what I did before. When I do pi, or when I do F and then pi, I get 0 back. Because what do? You start with some A and F, do F bay to it. That's in the image of F, and pi projects that to the 0 coset. So this is 0, which is of course F bar pi. Therefore, pi is in the image of F bar, which is the kernel of G bar. Because of the exactness of the Hom sequence. And so what this means is there exists a gamma in Hom C to V mod MF such that since the gamma G is pi. Right? Because pi, of course, is in the image of F, which is the kernel of G, then that pi must be in the image of G bar. Everybody okay with that? So, plug B into this. So pi of B lost the thread on this a little bit. So pi of B oops. I got to see where B was. Let B be in the kernel of pi. There we go. Not kernel pi, kernel of G. And of course, this is my big last thrust, so I want to show this is actually the image I have. So pi of B is equal to pi of B is gamma G of B. Well, B is in the kernel of B is in the kernel of G, so this is 0. Therefore, B is in the kernel of pi. Right? So B is in the image of that. Because if you look at pi, this takes B to B plus MF. So if it's in the kernel, that means that B is in the image of F. And there you have it. So anything in the kernel of G is in the image of F. Okay, any questions on that? This is a bit to absorb with all the functions playing around, but did y'all kind of get the gist there? Here is a theorem, and I will go through this one as well. And again, much of the heavy lifting is done for us. So notice that on this previous theorem, it's a great theorem, but the wings are clipped a little bit because you don't get the full exactness. And in general, you don't. Even if 0, A, B, C, even if that sequence is exact, it doesn't mean that the Hom sequences are exact, and vice versa. If the Hom sequences are exact, it doesn't mean that is. However, if the sequence splits, then you're good to go. There. 12.73. Following conditions are equivalent. A is split exact. B covariant Hom. 0 Hom split exact. For all D, for all R modules D. And C. Okay. So let's really think about what we need to show here. It's actually pretty, so we're gonna do this with the contravariant. Let's do A if and only if C. So suppose we have A, so we've got this split exact. We need to show that get a split exact sequence here. Now, what do we get from the split exact? Well, just from this part right here, we automatically get this. Right? So what I mean is split exact, it doesn't matter, just exactness gives me this much is exact, right? So exactness of A, B, C, 0 gives exactness of 0 home AD, home BD, let's see, home AD. Right? So really, I can make this easy in the following sense. It suffices to show there exists, let's say some K bar from home AD, home BD, such that such that when I do K bar and then F bar, this is the identity on home AD. That's really all I gotta show there. Everybody okay? This will get it in one fell swoop, because this will give that F bar is onto, because notice the identity function is 1-to-1 and onto. This will give that F is onto, so it will finish the exactness. And also this composition gives you the splitting back. Everybody okay with that? So this is really all we have to show. This gives onto F bar and splitting. So let's do it then. So there exists a K from B to A such that when I do KF, this is the identity on A. This is, of course, from the splitting this. There has to be a K that goes back to A that does this. Find Now, let gamma be in, home or AD. So gamma, some function from A to D. Notice that gamma Fk is equal to gamma, because this thing is wrong, didn't it? Kf. Gamma Kf is gamma, because this is the identity. And this is F bar of K. F bar of gamma K. And this is K bar, F bar, gamma. And so what we've shown is for every gamma in home RAD, this composition is 1. Therefore, K bar, F bar is 1 on home AD. So that gives you exactly what you want. That is to say, F bar is onto, and oh, did I do that right? Yeah. FK is correct. No wonder. Let's try this again. This is F bar gamma K. And this is, oops. What's wrong? Let's try this again. This is, yeah, it's supposed to be. Should be. Kmart. So let me go through this more quickly again before I do a big tree lab. So if you have gamma, a homomorphism from A to D, then F K gamma. So that goes from A to B, B to A, then A to D. So that's good. And this should be F bar gamma K. And this should be A bar, F bar, gamma. Let's see, does this make sense? Okay. Let's see, let's start with a homomorphism from A to D.
No, you want the F bar, K bar.
Right, so, yeah, I was probably, I think I was looking up here at this one instead of the bottom one. So let's see here. Gamma. Yeah, gamma is supposed to be in home RAD. Right, and so see, gamma goes from A to D, and then F bar. Okay, so this should be anyway. This is a silly mistake that I've made, so this will be easy to fix. I'll fix this next time. Somehow I've got this turned around here. I want the K bar to go from here back to here. So I want K bar and then F bar be 1 on home D. So it looks like I did that right. And anyway, I'll sort this out next time. Maybe you can beat me to the punch, but we'll finish it up next time. Any questions? Okay, I hope everybody can make it to the review session tonight. And hopefully I'll see you this afternoon.